Imagine standing in the middle of a hurricane. Now imagine that hurricane is made of superheated plasma traveling over 1 million miles per hour. That is what every spacecraft faces once it leaves Earth. Space is not empty, it is violent, filled with radiation, magnetic storms, and streams of charged particles blasting outward from the sun every second. These streams are called solar winds, and without protection, they could fry electronics, scramble communications, destroy satellites, and even threaten astronauts' lives. Yet somehow, our spacecraft survive. Voyagers still communicate from billions of miles away, and satellites orbit Earth every day while enduring constant attacks from solar radiation. So how do spacecraft survive one of the most hostile environments imaginable? The answer lies in one of humanity's greatest engineering achievements. The sun is not just a giant glowing ball in the sky. It is a massive nuclear reactor constantly exploding outward. Every second, the sun releases streams of electrically charged particles, mostly electrons and protons, into space. These streams form the solar wind, and they never stop. Solar winds travel at speeds between 250 and 750 kilometers per second. That's up to 1.7 million miles per hour. But speed is only part of the danger. These particles carry electromagnetic energy capable of disrupting electronics and damaging delicate spacecraft systems. During solar storms or coronal mass ejections, the sun can unleash billions of tons of plasma toward Earth and the rest of the solar system. The first line of defense, shielding. The first layer of protection is physical shielding. Spacecraft are wrapped in specially designed materials that absorb or deflect harmful radiation. One of the biggest threats is ionizing radiation. When high-energy particles hit electronics, they can flip bits in computer memory, corrupt software, or permanently damage circuits. To stop this, spacecraft use radiation-hardened components. These are specially engineered electronics built to survive intense particle bombardment. But electronics alone are not enough. Many spacecraft are covered in aluminum, titanium, or composite shielding layers designed to reduce radiation exposure. NASA's Orion spacecraft even uses water and polyethylene materials because hydrogen-rich substances are excellent at blocking radiation. But some missions face temperatures so extreme that normal shielding would instantly melt. That's where things become extraordinary. The most advanced heat shields ever created is called the Thermal Protection System. It is 4.5 inches thick and made from carbon-carbon composite foam sandwiched between reinforced carbon panels. Despite its size, the shield is surprisingly lightweight, and it works because carbon materials can withstand enormous heat without melting. The side facing the sun becomes white hot, but just inches behind it, the spacecraft stays cool enough for normal electronics to operate. The probe also constantly rotates itself to ensure the heat shield always faces the sun. Even with advanced shields and software, solar storms are still powerful enough to threaten spacecraft. When scientists detect massive eruptions from the sun, spacecraft are often placed into safe mode, shutting down non-essential systems to survive the radiation blast, while astronauts aboard the ISS move into more protected sections. But does that mean spacecraft are completely safe from the sun? No, because solar activity is unpredictable, and even our best technology can only reduce the danger, not eliminate it. That's why every mission is carefully timed around the sun's 11-year solar cycle. Humanity has built incredible machines capable of surviving radiation, fire, and plasma storms. But exploring deep space is still a constant battle against the fury of our own star.